basically we can do that. But we find out we can get the gain by simply scaling. There's only one feedback resistor, RF. So if we want to have different gains, we would need to scale this resistor RC. S1, S2, and one of the S in here. And this is basically the equation. If we make all the resistors RS equal, then we just get an amplifier times the sum of the different inputs. Now it turns out this is a trigonometric sum here. So if we take an example here, this summer or linear combiner has two channels on the input, and it's connected to 9-volt battery. These batteries are all wired directly to the op amp pins, so that the 10K feedback resistor, the two source resistors, RS, are equal to 10K ohms. So what's the gain of this amplifier? What is it? So the ideal gain is minus RF over the source resistance, so minus 10K over 10K plus is minus 1. And then on the inputs though, the inputs here, one input said an amplitude of 1 volt and a frequency of kilohertz. And the second input has an amplitude of 0.5 volts and a frequency of 4 kilohertz. So these are tones that the summer is going to combine into one output over here. And then the batteries here are plus minus 9 volts. So to extract or examine the output of the summer, we can set up a simulation profile. And here, the highest frequency is 4 kilohertz, so we'll let run to 4 milliseconds. That'll give at least 4 cycles. And then we'll reduce the size down to 10 microseconds. And that basically is it to set up the ambient. And then we'll put an automatic plotting pin on the output, the out. So basically, so we don't have to add a trace when this actually completes the simulation. So that as far as wiring the circuit up, it appears to be wired without errors, but we won't confirm that until we actually run this first simulation here. Now this is the output of the summer. So the first question is, does this make sense? The schematic is sine waves going into the combiner of the summer, and then the output is not really expected. It's definitely not sinusoidal, but we will explain why the output has this particular, probably the shape of it first, and then we get into the amplitude.
It had to do with the frequency.
What is the summer doing?
It's adding two different sine waves together.
And how is it doing it?
Is it convolution?
What is it?
I think convolution.
It's,
Or-
well, the sine waves basically have their phases. So each one has an amplitude and has a phase. And both of these sine waves are we'll assume there's zero phase. We can, if we open the component page, there's no phase. We could add a phase in there, but there's no phase, so it goes start at zero. So as these waveforms pass through the combiner will add them according to their phases. Or go back to algebra, it will add them together. And when it does that, basically we get this unusual waveform appearing on the output. So the question though is still, is it actually operating properly? So if we go back to the formula for the combiner, V out is minus R over R is 1 times the first source minus R over R is 2 minus the second source. Then basically, the way to kind of confirm this equation would be to make the two inputs, we want to make the two inputs the same. If we go back to our schematic, and we'll change the first source to 4 kilobits. So, what type of output do we expect now?
The sinusoidal wave of magnitude of amplitude 1.5.
So we've got one source is still 1 volt, the other source is a half, they're still the same frequency. So now the output appears to be, if the sinusoidal, we can assume it's 4 kilohertz, and then the combiner is adding 0.5 to 1. We're trying to find out if this makes sense. So when the combiner adds them together, we'll put a marker in the peak here. So it's saying it's 1.49, 1.5. So this drawing, this output then, it's confirming this equation right here. One has an amplitude of 1, the other has an amplitude of 0.5. So the combiner appears to be working properly. Now, so here's your first example here. You have two signal sources. One is VS1 and the other is VS2. We want to create an output signal minus 10 VS1 minus 10 VS2, which gives minus 10 times VS1 plus VS2. So go ahead and make an attempt to draw a schematic. It's heavy as a math circuit, so draw the schematic of your circuit. Now, it's not giving information in regards to what the actual circuit should be. So the way to decide on the circuit is basically the way the equations are formed here. So we notice when the two signals are combined with each other, they're both inverted. There's inversion here. So that would be an inverting op amp. Also, when the two signals are combined, they both have a gain of minus 10. So we have an inverting amplifier and two inverting amplifiers. Each one has a gain of 10. And you could design it as two separate optics, but the combiner allows us to combine these into one circuit and then basically get the gain of 10. So design a circuit. It says to design a circuit, select the resistors, select the power supply voltages, and then show all of your calculations. So again, this is kind of a typical exam question here, where you have to design the circuit design
From
schematic.
the game we get the RF or RS. So minus 10 is RF is 10K and RS1 is 1K.
And then if someone, resistors greater, 1K ohm or greater. So if someone wanted RF with 100K and RS 10K, that would still give, you'd have to decide if that's actually a gain of 10. So it says to show all your calculations after selecting resistor. It also indicates find a power supply voltage. So assume we need a summer, so we're going to select resistors greater than 1K ohm. So here's an example schematic, and basically our batteries are arbitrarily here are 12 volts, and they're symmetrical, and this design is using 10K feedback and a 1K series resistor. And now, in order to simulate the circuit, the designer has to, let's say it's given that the input are both 0.5 volts here. And we notice the two frequencies are the same. So you have to sketch the out. What would it be?
The sine wave of amplitude 1.
You're gonna sketch the output.
Sketch the output.
Yeah. Or just simply, or is that 0.5? Oh, yeah, do you want? At least. Oh, what? The amplitude?
And so we're predicting the piece by what would be correct for piece by. However, at the same time, our assumptions may not be accurate. So two inputs at 0.5 amplitude will add together to 1 volt, and then the frequencies are the same. We should get a sine wave output with the amplitude of 1 volt. And what is that peak to peak? It's 1 volt amplitude, and what's the peak to peak?
10.
10?
One goes to 1 volt, then goes to minus 1 volt.
It would be 2.
So is that 2 volts peak to peak?
It would be 1 minus 1.
Yeah.
From the 1 to the minus 1, it's 2.
Is that 2 volts peak to peak?
2 volts each.
So we're basically predicting what these guys should come up with here. So we have our equation for the liner here. And we set power supplies of plus and minus 12 volts. And we select resistor. Our feedback is 10K, the two source resistors are 1K ohm. So the design is pretty much complete. And we provide an input. In the simulator is going to use this form of the input. That's what these generators are. Minus 10 sine 25, 1000 T. So math, on paper, once you completed your design, You take this equation and then insert
That's
the input
hold it down.
form and then calculate. So P-Spice should plot minus 10 sine 2 pi 1000 t. I think we did pick up, there's a gain of 10 here. So 10 times 0.5 is what?
Fine.
So what should the actual peak to peak be out, be coming out?
20 feet to feet?
The voltage is high.
It's going to be 10 volts,
Technically, it's on the some of that.
10 volts on the peak and minus 10 on the negative peak.
It's 20.
It's 20.
So it's 20 volts peak to peak. So on the scale here, and these are just stacked piece-wise plots. The inputs are on a separate plot because they're so small compared to the output. But the output plot is at the bottom, it's going from 10 volts to minus 10 volts. So it's 20 volts peak to peak. And then the two inputs are 500 millivolts peak, and they're both in phase with each other. And then we note the output is 180 degrees out of phase with the input. So that means we're getting the inversion, the gain is 10, and this appears to be a 1 kilohertz waveform here. So there's basically, so what you have here is you have the specification of what it is you're trying to design, and then you have 3 parts of it, A, B, and C. And now draw your schematic, and then calculate the resistors, decide on the power supply, and then mathematically predict what the output should be. So this is similar to the homework assignment, where on paper you predict P-Spice output without having P-Spice actually complete the work for you. So, and if you don't get agreement with P-Spice, and then keep in mind that if you don't get agreement with P-Spice, which one is correct, your work or P-Spice?
You would have.
You get a difference between your paper calculation and P-Spice simulation results. So which one is correct?
The computer.
You'd have to look at the two and decide, and then eventually come to a conclusion on which one.
Now, is P-Spice always correct?
No.
Probably more so than me though.
How we do it's not always correct?
User error?
Who generated the error?
Oh. Yes.
So we're going to assume P-Spice is correct. Whatever information P-Spice is providing, it's due to the information it was programmed. And so that means it comes back to the engineer. There's an error, basically, it looks like P-Spice is giving a user result, that usually goes back to the engineer, and you have to go back and redefine your work. So here, P-Spice would agree with the prediction in that equation. And another design, this one says to create V out is 5 times VS1 minus VS2. And now, basically, the difference here is we're asking the linear combiner to perform a subtraction. And then, in a subtraction, one of the signals needs to be inverted. VS2 needs to be inverted. Yeah. And VS1 is not inverted. They both have the same gain of 5. So how do we design a combiner that inverts one of the two waveforms on the input?
Yeah, you use two, yeah. I mean,
So if this appears on a question like this appears on the midterms, and it will, there will be a combiner on the midterm that requires a subtraction. This is the only information that will be given. Equation. You need to create an output signal according to this equation. And this is a kind of some hints here. This is a proposed circuit. It says that in order to do no inversion and then inversion, we should use at least two op-amp circuits. But the question is, how do we put the op-amps together? The first op-amp, we decide is going to be an inverter. It's just going to invert the input signal. And a non-inverting op-amp will not be the best choice here because of this inversion here. So, not given the circuit, you would basically be trying to come up with some combination. So this inverter at the first stage, it will invert only the first source here. And then we notice BS1 has a positive sign, so we need a second inverter to remove that negative sign on it. So we'll get a positive BS1 out, and BS2 is subtracted from BS1. So the way we can do that is we can add a second op-amp, which is what? What is this op-amp?
Non, ops,
Invert.
non-inverted.
It's a summary?
A very combination inverter. This is our summer. So the summer is going to be used to add in V sub S2, and it's going to invert it before passing to V out. So the summer is going to have two functions here. It's going to invert V sub S2, and it's going to invert V sub S1, which has a negative in front of it. So it's going to combine them at one stage. So with that, your next step would be to select the resistors and also select the power supply. So I'll leave this at this. I'll leave this question at this. And as I said, more than likely something like this will appear on the midterm. So the circuit is only partially designed right now. You have to basically now go in and decide how to manage the resistor values in order to get this equation with the gain in it here. And this, if we take our combiner or summer, another application we can bring up is a level shifting amplifier. And to get a level shifter, we take our combiner, converter, and we put an extra battery in series with one of the inputs. So the purpose of the level shifter is to, if I have an input, some small input like this, and I want the output to be larger not only larger, but I wanted to have different peak and different minimum on it. So then this level shifter is going to will scale the input to some arbitrary output. And if you, which question in homework 1 is a level shifter? It's problem 2 or 3 in homework 1. One of them, the 2 is a level shifter. So this is covering design of the level shifter. So this circuit, basically, the equation of it is basically similar to a linear combiner at the bottom. This is the equation for the level shifter. And the difference from the combiner is that the level shifter has a battery called V sub R attached to the second input here. And that's the only difference from a combiner. But the idea is to, how do we actually get this circuit to scale this input V sub S just using this extra battery? Without going back over the combiner, we could just go right ahead and come up with a problem. And this problem is similar to your homework. One of the problems in your homework 1. It actually reads very similar to it. So it says create a sinusoidal Vn. So first you have to create this input. Minus V off is equal to the last digit of your Z number. The amplitude, so you're basically creating the input waveform. The amplitude of this waveform is 2.5 volts. The frequency is 3 kilohertz. And what is your V off? And in a transient analysis, the V sine source has a V off. So you would click on that and set a minus V off number according to the Z number that is specified. And the circuit then, so you basically, this is part of the sum. You have to create your own distinct input source. So the paper design is, that means that in all of your homework, there should be no duplication of effort because you have, the only case if you have a duplication in the last digit of the Z number. So design a level shifting circuit such that the lower peak of Vn is shifted to 8 volts and the higher peak of Vn is shifted to minus 5 volts. And then so this is your paper, this is the paper design. Once we have the paper design, show by means of piecewise time response, which is transient, that your circuit really works. And this design is using 2 15-volt batteries, and then make sure to explain every step in your design. So given a proposed circuit, which is here, and then given the equation for the level shifter output, this is basically the problem that it's asking to create here. Now the input amplitude is 2.5 volts. You would need to draw your input. You probably don't want to draw it on paper. In piecewise, you can draw it by setting up your transient. So if we take this circuit then, so the amplitude is 2.5. So let's say so we set the amplitude to 2.5, and then just pick a last number for a Z number. Any number.
1.
1. So the offset then is -1. And the frequency, we'll leave it at that. So this has a DC offset of -1, the amplitude is 2.5, and we'll run the simulation just to find out what the appearance of the input. So I'm here. So we're going to plot that waveform. So the waveform that has the offset on it is here. And your homework assignment, you'll need to verify in PSpice that you have created the correct waveform. So this so here VN, and we'll mark it. So it has a peak of 1.46, which is probably around 1.5. And this says the amplitude is 2.5. So going back to the simulator, on this lower waveform, we'll go back and we'll make the offset equal to just 0 first. So this is the waveform without the offset. You're trying to make sure your assignment makes sense that you're going to submit. So the top, this waveform then, so this peak is 2.4, the peak is 2.5. If we offset this by -1 volt, what will the peak change to?
1.5.
1.5. So we go back and then we'll change it to this -1, the last D part of the D number. And here it did move. And again, and it says 1.45, which is, basically, that's close enough to 1.5. So that part of the problem, the design, at least for that number -1 is completed here. And we verified PSpice agrees with that. And now it says design level shift in circuit. It's when you shift the lower peak to 8 volts, and the higher peak is going to minus 5 volts. So it's going to flip the input and convert it into a very different waveform. It should still be a sinusoid. The batteries are going to be 15 volts, so you don't want this amplifier to go into clipping. But when you design the level shift, you understand that it is going to invert the input according to the spec that you have here. And you can draw on paper before you start this problem in the homework. Draw on paper what you expect the output to appear like once you complete the design. And that way you're prepared to not just accept piece-based results, but you basically can confirm that it should work as your paper design is expecting it to. So the purpose of the level shifter is to scale or amplify a source to a DS min, and it has a DS min and a DS max, and it will change it into a new V out with 2 new upper and lower limits. So over here, here's a source on the input to the level shifter. It has a DS max and a DS min. We pass it through the level shifter, and what comes out is a new waveform. It has a new V out max and a new V out min. And if we're assuming this is inverting, that's fine. But if we want a non-inverting level shifter, that's a different design from this. So if you say, well, where would a circuit like this be useful? In temperature sensors usually have a very small voltage output from it, and it's probably too small for an analog to digital converter circuit to basically use it. So you have to amplify the output of the temperature sensor. So this equation, the level shifter is this part of the equation. Minus RF over R1 times V sub R. And the gain of the level shifter is minus RF over divided by RS. And that's the peak-to-peak output divided by the peak-to-peak input amplitude. So you take the peak-to-peak output and divide it by the peak-to-peak input, and that gives you the gain that we need from this level shifter amplifier. So this now does bring up something to consider. How many batteries are on this schematic now?
2.
It's 3. And also, batteries are expensive. We want to design a level shifter that will operate off of either the plus battery or the minus battery. And that way we can remove an extra battery. So, however, a level shifter, if it's shifting up, it uses a different polarity battery whether if it's shifting downward. So we have to decide, are we going to set that extra battery to the plus battery, or are we going to set it to the minus battery? And it will usually be going to be obvious if you basically have picked the wrong battery, because you find that your output is basically flipped compared to what you expect it to be. So this is not an issue. We just said that we'll use one of the batteries for this piece of our level shifting input. So if we want to shift upwards, then this equation minus y for R1 times VR must be positive. At the same time, in order to shift positive, that reference battery, we want to use the negative battery. Now, what's the explanation for that? minus V sub R to the negative battery,
The input is getting inverted.
because it's inverted. It's a logical reason to do that. And then the opposite is, if we're shifting downward, again, it's going to invert, so we'll tie this extra battery to the positive batteries being used. So we notice the reason for that then is basically this inverting amplifier in the circuit. So, now it's a good idea to, as a homework assignment, not to turn in, but to go through this design and become convinced that it actually works. As part of the homework assignment, is your individual project has to be convincing that it actually works. So, again, we're going to start with a device that generates a really small output voltage. So the temperature sensor. The temperature sensors usually, they're very small devices and they respond to room ambient temperature, and they can generate very small millivolts output. But at the same time, if we have a analog to digital converter or microcontroller can't deal with tiny input voltages. They want something larger. So we'll assume that our temperature sensor, the lowest temperature when it reads it is 30 millivolts, and then when it reaches the highest temperature, the largest output is 50 millivolts. So what if the lowest temperature is minus 30? So this is minus 30, and then the highest temperature is 100. So how many steps do we need between 30 and 50 millivolts to produce an output sense of temperature from 30 to 100 degrees? You're talking about the resolution of it. So you're looking at microcontrollers and devices, and you're trying to decide the number, the binary digit that you need to read this temperature sensor. So you've got 30, so it's 130 degree temperature change, and only a 20 millivolt change in the sensor output. So you need something that can detect. If you divide those two, it means that you're going to need even much smaller than a millivolt, a fraction of a volt at each temperature. So it's not readable unless even the most, probably the most expensive analog to digital converters cannot read voltages with that kind of resolution. So here, the engineer decides to the A to D converter, let's say it wants to have an input of 0 to 5 volts. So we need to convert 30 millivolts to 50 millivolts. We want to convert that to 0 to 5 volts here. Now for the digital part, if we have an integrating analog to digital converter, its full scale input is 5 volts. What information do we get from this? This is your logic design, the digital part. What information does that tell? We have a 10-bit digital slope integrating analog digital converter. Its full scale input is 5 volts. So what's the meaning of 10 bits mean 2 to the 10? 1,024 levels, is that correct?
Yeah. Mm-hmm.
And we can get a 12-bit or a 16-bit, depending on the cost. This says that our AV converter can sense 1,024 levels with that device. So full scale of 5 volts means divided by 1024, it means each level is 4.88 millivolts. Now the sensor can only detect 20 millivolts to 50 millivolts. So how many temperatures would this sense?
Can you repeat the question one more time?
You're going back to your temperature sensor. Its output is 30 millivolts to 50 millivolts. That's it. The temperature range is 130 degrees, you're saying. So when we go to design our digital part, the full scale for this 10-bit AD converter is 5 volts over 1,024 levels. The full scale is 4.88 millivolts. So our 30 millivolts corresponds to 30 millivolts divided by 4.88 millivolts, which rounded up to 6.2. 50 millivolts corresponds to 50 millivolts divided by 4.88 millivolts, and we round that up to approximately 10.3. So you might expect, here you had to step out of electronics and go back to your digital circuits to basically get an idea of how we should proceed here in order for this circuit to actually work. Now your homework assignment, you won't have to do that. We're just assuming we're trying to deal with a real world analog to digital converter. This is this practical?
Yeah.
It's saying that from 20 millivolts to 30 millivolts, to 50 millivolts, that's 30 millivolts. So we divide 30 millivolts by 4.88 millivolts. How many temperatures can you say? You can say, if I divide 30 by 5, so that means I can sense only 6 temperatures with this system. So, as far as the digital is concerned, this will work. The problem comes in these numbers here. They're not 0 to 5 volts here. So we need to find a way to expand this 4.88 millivolts by making it smaller and then making the output physically larger. So we kind of come into a conclusion here. Our digital is going to work. However, the AD converter will only detect 6 or so temperatures in this stock. We have at least 130 temperatures %. So the result here is try this again with a level shifter. And we're going to shift the temperature sensor, go from 0 to 5 volts. So 0 millivolts corresponds to 0 or 4.88 millivolts, which is 0. 5 volts corresponds to 5 over 4.88 millivolts, which is approximately 1,024. So we can convert the temperature sensor to go from 0 to 5 volts. The AD converter will receive the difference here, 1,024 levels. And now we have a workable system right there. So this part in the middle, this is, we went through the calculation, but it just indicated that we only can sense probably 6 temperatures. Now we can sense a lot more temperature. So how do you design the AD converter? And here's our result here. Over here is our sensor. Remember, we're still on paper. This is our sensor, our level shifter with an amplifier, our AD converter, and then we take the output of AD and run it through the computer and process the information. So the first step is the gain. What's the gain of your level shifter here? It's the maximum output divided by the minimum, the max input minus the minimum input. So in order for this circuit to perform, we need a level shifter with a gain of 250. In your homework assignment, you're going to have your own individual gain that you use. How do we get the gain of 150? That's the simple part of the design. We scaled two resistors to get a gain of 150, 250. So we let RF equal 250K and RS equal 1K. We'll amplify the source up by 250, and then we're going to invert it. Now, this inversion, though, we have to basically reflect, are we flipping the input up or down? So we'll leave this inversion in here for now. So this is the simple part of the assignment. We have the gain of the amplifier. Next, we want to draw a what-if diagram, because we want to go inside the op-amp, the level shift, to understand exactly what's happening. So because of the inverting amplifier, the upper signal, what is it mapping here?
That'll be when it activates, when it gets that.
It's projected or something to a different number. So the upper signal is mapped to the lower output as shown. So on the level, on the temperature sensor, the 30 millivolt low temperature gets mapped to 5 volts on the output, and then the 50 millivolt high temperature gets mapped to 0 volts. So this is the level shift. This is the simplest explanation of how this circuit works. The level shifter is going to invert the input waveform. So that means there's something else in here. This isn't the level shifter yet. This is kind of a what-if circuit. So now we're going to put the level shifter in the diagram. Now to get the level shifter, we have to find the amplified levels of the maximum and minimum input signals. First, assume there's no level shifter. So we're going to set that level shifter battery to 0 volts. And now we're going to plot what the output of the amplifier appears to be. So the output with 50 millivolt input is minus 250 times 50 millivolts minus 12.5 volts, and then the output of the level shifter with 30 millivolts input is 250 times 30 millivolts inverted minus 7.5 volts. So that's in here somewhere in the op-amp. In this stage, these are actually the levels that we're getting out of the circuit. We're not getting 0 to 5 volts. We're getting these two levels. So now the level shifter has to shift these voltages to 0 to 5 volts, these intermediate voltages. And now again, you can draw your map of your circuit here, what it's actually doing. So over here, 30 millivolts is shifted or mapped to minus 7.5 volts. And now we need to level shift this to 5 volts. The 50 millivolt input is mapped to minus 12.5 volts, and we need to level shift this to 0 volts. Once we complete that, we'll have an output that goes from 0 to 5 volts. And this is the diagram that's saying your circuit will work properly. So with this, these numbers here. The difference between these numbers and the difference between these two numbers.
Negatives?
It's,
The difference,
it's the rate on the bottom?
the difference,
Oh,
12.5?
12.5. They both are equal to 12.5, so that means a single level shifter will work as long as we have symmetrical battery on the op amp. So the bottom says, now we're going to put in this battery, and we're going to shift minus 12.5 to 0, minus 7.5 to 5 volts, which is a difference of 12.5. So we set up the level shifter equation, this part of the equation, minus 250, which is a gain over this resistor, times V sub R is equal to 12.5. And here, we already have R1. We solved for that when we started. So now we decide which battery do we connect V sub R to. Do we connect it to the negative battery or do we connect it to the positive battery?
The negative?
Positive.
As I say, positive battery. This is saying V sub R is negative. And this should be 250. No, that's R sub 1. This is the resistor in the resistor in here. So let's take this, and it's a multiplication here. This is inverting, and V sub R needs to be an inverting in order to get a positive 12.5. So we put negative 10 volts here and solve for the resistor. We get R1 is equal to 200K. I'm going to pause here. So your homework assignment then, and this is not going to be handed in. The homework, enter the schematic into PSpice, build it. R1, RF is 250K, RS is 1K, R1 is 200K. The extra battery is tied to the negative 10 volts, and then confirm that the circuit actually works in your own simulation. And what you should be getting is, you'll need to build this circuit here. You'll have to create a circuit, a source that goes from 30 millivolts to 50 millivolts. There's a couple ways to do it. You can do it with a sinusoid, or you can do it with a pulse. But I'll let us explore PSpice to decide on that. All right, that's what we'll cover this